Welcome to the walkthrough for worksheet number 4. Today I'm going to tell you how to find the empirical and molecular formula of a compound. And on the front of the worksheet, we're just finding empirical formulas. Empirical formulas are the simplest ratio of elements in a compound. So we're trying to figure out how many, for example, in this first problem, how many bromines to how many magnesium atoms are in the compound. And there are two steps to finding an empirical formula. Step one is you need to convert all of the elements in the compound from grams to moles. And then step two, which I will do in a different color, I'll do it in red. Step two is to find the mole ratio of those elements. And the way you do that is you divide by the smallest number of moles of the elements in the compound. All right. So let's look at this first problem. Find the empirical formula of a compound containing 32 grams of bromine and 4.9 grams of magnesium. Draw a particle diagram representing this compound. So our first step was to convert grams to moles. And we're told that we have 32 grams of bromine. And we know from our previous math that to convert from grams to moles, we need to use the molar mass, which we find on the periodic table. So when I looked up the periodic table, I looked up bromine, and I found it has a molar mass of 79.9 grams per mole. So I'm going to set up my train tracks here. And because I know that I'm starting with grams and ending with moles, I want to write the 79.9 grams on the bottom of my train tracks so that my grams will cancel and I will end up with moles as the units for my answer. So when things are on the bottom of the train tracks, we divide, and if on the top, we multiply. So we take 32 times 1 divided by 79.9, and that gets us to 0.401 moles of bromine. And then for our second element, magnesium, we have 4.9 grams of magnesium. And again, I will set up my train tracks, and I looked up magnesium on the periodic table, and it was 24.3 grams of magnesium in 1 mole of magnesium. And again, I knew to write the grams on the bottom so that they could cancel. And when I divided that, because it's 4.9 times 1 divided by 24.3, I got 0.202 moles of magnesium. So that was my first step, converting grams to moles. Now my second step is to figure out the mole ratio, because these numbers, it might not be immediately obvious to you what the whole number ratio is. And we know from Dalton's theory of the atom that all compounds have a whole number ratio of elements. So to find our whole number ratio, we will divide by the smallest moles, which in this case is magnesium. When we divide by the smallest moles, that means we set the ratio of the element with the fewest number of atoms to 1, and then we see how many of all the other atoms there are. So we divide both these by 0.202, and that leaves us with a ratio of 1 mole of magnesium, and the smallest one will always end up as 1 since we're dividing by the smallest moles, and it leaves us with a ratio of 2 moles of bromine. Now you may notice that's not perfectly 2 on the nose, but as long as it's within about 1/10 plus or minus 0.1, you're allowed to round it to the nearest whole number. When we get to number 6 on the back, we'll talk about what happens if it does not come out to a whole number. But for these first problems, it will always come out to a whole number. All right, so we have 2 moles of bromine to 1 mole of magnesium, which means our empirical formula is going to be Mg, just one of them. We don't have to write the one though, Br2. Now, for regular chemistry, we don't focus on naming. You could write it as Br2Mg, and that would get full credit. In general, if we have a metal and a nonmetal, it's traditional to always write the metal first. And you know it's a metal because it's to the left side of that dark line on your periodic table. But again, I would accept it both ways for this unit. So that is our empirical formula, and then it asks us to draw a particle diagram. And when we draw our particle diagrams, we want to represent the relative masses in our particles. So we know from the molar mass that magnesium has a much lower mass per atom than bromine does. So I'm going to draw my magnesium as sort of a smaller circle. And then my bromine, I'll change colors just for fun. I will draw as sort of a bigger circle. Because it has a larger mass, and we like to use the size of the circle to represent the mass of our particles. Okay, on question number 2, excuse me, it's similar to the first question. What is the empirical formula of a carbon-oxygen compound given that 95.2 grams of the compound has 40.8 grams of carbon and the rest oxygen? Draw the particle diagram. So since they only give us the carbon and not the oxygen, our first step here will be to subtract just to figure out how much oxygen we have. So we're starting with 95.2 grams of the compound. That's our total mass. And we will subtract the mass that they gave us for the carbon. And since it's just carbon and oxygen, what's left over is the mass of oxygen. Now we can do what was our step 1 before, which is converting grams to moles. So we have 40.8 grams of oxygen. 40.8 grams of carbon. And we will look at the periodic table to convert it to moles, and we see the oxygen is 12.01 grams. Did I say oxygen again? I mean carbon. For 1 mole of carbon. So our grams cancel. And that ends up being 3.4 moles of carbon. One nice thing, if you don't like your doing sig figs very much, is sig figs aren't really important in this type of problem because they end up as a whole number ratio. There's no answer with sig figs, so you don't have to worry too much. You don't want to round overly much, but you don't have to worry about sig figs. So we have 3.4 moles of carbon, and then we will convert our oxygen. So 54.4 grams of oxygen to our train tracks. Oxygen, the periodic table tells us, is 16 grams per mole. So our grams cancel and we get moles of oxygen. 54.4 divided by 16 is also 3.4 moles. So it turns out that these are the same. So I can do my mole ratios. I'll do my second color here. I'm dividing by the smallest, but of course they're the same. So that's the same number, which means that I end up with 1 mole of carbon and 1 mole of oxygen. And that means that our empirical formula is 1 mole of each, or CO. And when we draw our particle diagram, carbon has a molar mass just a little bit smaller than oxygen. So I'll draw a circle for carbon, and I'll draw just a little bit bigger circle for oxygen. I'll color that in too, because that's hard to tell the O from the circle, huh? All right, so there's my particle diagram. All right. Okay, so now let's do the last one on the front here. And this one is pretty similar. The only difference now is that we have 3 elements. So our compound has 9.8 grams of nitrogen, 0.7 grams of hydrogen, and 33.6 grams of oxygen. So what is the empirical formula? Our first step is the same as the previous ones. We convert from grams to moles. So we have 9.8 grams of nitrogen And the periodic table tells us the nitrogen is 14.01 grams per 1 mole. And again, as in all the previous problems, we know that we have to put the 14.01 grams on the bottom because we want our grams to cancel and get moles for our answer. So we multiply by the 1 on the top, divide by the 14.01 on the bottom, and we get 0.70 moles of nitrogen. Then the hydrogen is 0.7, so 0.7 grams of hydrogen. Do our train tracks. Hydrogen is 1.01 grams per mole. And so that ends up being 0.69 moles of hydrogen. And then finally, we have the oxygen, which was 33.6. And oxygen is 16 grams per mole. So our grams cancel, and we get 2.1 moles of oxygen. So our second step is the mole ratio. Now here, nitrogen and hydrogen are essentially the same number. Hydrogen's a teeny bit smaller, so I'll divide by that number, 0.69. And when I divide, you end up with 1 mole of nitrogen, 1 mole of hydrogen, and finally 3 moles of oxygen. That means our empirical formula is a 1:1:3 ratio. And so our empirical formula would be HNO3. And as I mentioned earlier, we're not going to be picky about the order you write things. If you wrote that in any other order, it would be fine. For my particle diagram, nitrogen and oxygen are pretty similar in size, but hydrogen's a lot smaller. So I'm going to draw a nitrogen. That will be my nitrogen. I'll do red for oxygen, and there's 3 of those. And there we go, nice oxygen. And then I'll do black for hydrogen. So just 1 small hydrogen. All right, so there's my particle diagram. Okay, on this side of the worksheet, we're going to be finding not just the empirical formula, but also the molecular formula. The difference is the empirical formula is the simplest ratio. The molecular formula is the actual formula of the compound. Sometimes the empirical and molecular formula can be the same thing. For example, water, H2O, is both the formula of the actual compound and the simplest ratio. But other times, the formula of the compound can be simplified to a simpler ratio. The example we used in class was glucose, which is C6H12O6. That's 6:12:6 ratio, but that can be simplified to 1:2:1, which is CH2O. So when you have a problem where you have to find the molecular formula, the first step is to find the empirical formula. So follow the process that we did on the front. EF here stands for empirical formula. And then the second step is to find the ratio of the molar mass of the actual molecular formula to the molar mass of the empirical formula. So the molecular formula molar mass, MF for molecular formula, MM for molar mass, divided by the empirical formula molar mass. Because the empirical formula will always be a simplified ratio, which means the molecular formula will always be a whole number multiple of the empirical formula. Sometimes that whole number might be 1, but the molecular formula will always be 1 times 1 or times 2 or times 3. It will always be whole numbers. So let's do an example to see how this works. So our first one, we have a compound of hydrogen and oxygen with 0.59 grams of hydrogen and 9.4 grams of oxygen. The molar mass of the compound is 34 grams per mole. We define the empirical and molecular formulas. So for the empirical formula, as we saw on the first slide, the first thing we need to do is convert grams to moles. So we'll take our 0.59 grams of hydrogen, and the periodic table will tell us that hydrogen is 1.01 grams for every 1 mole. And we know we need to put that on the bottom so that our grams cancel. So we divide and we get 0.584 moles of hydrogen. And remember, sig figs are not important on this particular scale. You don't want to round too much because you don't want to mess up your answer, but there's no sig figs in the final answer. And then we have 9.4 grams of oxygen. And oxygen is 16 grams per mole. And that gets us 0.587 moles of oxygen. And now we find the mole ratio. We divide by the smallest number, but you may have already noticed these are, although they're not exactly the same number, they're very close to the same number. We won't have anything that's not a whole number ratio until number 6, and I'll talk about how to deal with that at the time. But we end up with a 1-to-1 here, 1 mole of hydrogen to 1 mole of oxygen, which means our empirical formula is going to be HO, and I will draw a particle diagram of that. Now, hydrogen has much lower mass than oxygen, so I'll draw sort of a bigger circle for oxygen, and then I'll change colors here. Let's go to black, and a small circle for hydrogen. And now we get to the new part, which is how to find the molecular formula. So we need to know the ratio of the molar masses. Now, in the problem, we were given the molar mass of the compound, which is 34 grams per mole. Now, we need to see basically what multiple of the empirical formula is the compound. And the way we're going to do that is first we have to find the molar mass of the empirical formula. So the empirical formula is OH, which means to find the molar mass, we will take 1H, that's my H, and we will add 1O. And when you add those two things together, you get that it's 17.01 grams per mole. And we were told in the problem that the whole compound is 34 grams per mole. Now, what we know from just looking at that is that the molecular formula is not the same as the empirical formula. If it were, those two numbers would be the same. So what we do is we take the one given in the problem, the molecular formula of the molar mass, which is 34 grams per mole, and we divide it by the one we just calculated, the empirical formula molar mass, which is 17 grams per mole. And this will always equal a whole number because it's always a whole number multiple. In this case, our whole number is 2, which means that the molecular formula is twice whatever's in the empirical formula. So we will multiply that times our empirical formula, as in double all of the atoms in the empirical formula, which gets us a molecular formula of H2O2. And if we're going to draw that, I had red circles for oxygen, a little low on space here. I'll draw it. How about in this space right here? So 2 red circles for the oxygen and 2 black circles for the hydrogens. Now notice it's just 2 empirical formulas stuck together. This is the actual real formula. In this case, it's hydrogen peroxide. And what this means is the formula of hydrogen peroxide is H2O2, but the simplest ratio of its elements is just 1H and 1O. It's a 1-to-1 ratio. All right, let's move on to the next one. Okay, so this one, we're given the elements, rather than giving it in grams, they give it to us in percents. So we have a compound with 14.5% carbon, 85.5% chlorine, and then it gives us the molar mass of the compound. Now, don't worry, when you're given percents, you should always just assume that you have a 100-gram sample. Why is that? Because we could have any amount of this sample. We know that compounds have the same formula no matter how much or how little of the compound you have. And if we assume that it's 100 grams, 14.5% of 100 is 14.5 grams. 85.5% of 100 is 85.5 grams. So you can see we just changed the percents to grams. So now that we know that we can just change those percents to grams, we can do our calculations. So our first step is always converting grams to moles. It's often said in chemistry, when in doubt, convert it to moles. So we have 14.5 grams of carbon, and carbon is 12.01 grams for every 1 mole. And we put the 12.01 grams on the bottom so that it cancels. And that gets us 1.21 moles of carbon. And then we have 85.5 grams of chlorine. And remember, it's always chlorine, never carbon iodine. When we look that up on the periodic table, we find that it's 35.45 grams of chlorine for every 1 mole of chlorine. And our grams cancel. Oops, I forgot to write grams there. And that gives us 2.41 moles of chlorine. And then, of course, our next step is to find the mole ratio. We divide by the smallest number, which in this case is 1.21. And that gives us a ratio of 1 mole of carbon to 2 moles of chlorine. So our empirical formula is 1 to 2, so it's 1 carbon and 2 chlorines, CCl2. So I'm going to do a black circle for the carbon, and then chlorine is a lot bigger, so I'm going to do green and do kind of a bigger circles for the chlorine. So that's my chlorine, and that's my carbon. All right, so we found the empirical formula. Our next step is to find the molecular formula. And remember that we need to find the ratio of the compound molar mass that was given to us in the problem and the molar mass of this empirical formula. So we need to calculate the molar mass of the empirical formula, which means I need to add together. I have 12.01 one of those for my carbon, and then I have 2 chlorines, so 2 times 35.45 for the chlorines, and that will get me a molar mass of 82.91 grams per mole. So we can tell just by looking at it that's not the same as the one given in the problem. So we'll take our molar mass of the compound in the problem, 165.82, and we will divide it by the one we just calculated, 82.91. And that gives us the whole number ratio, which is 2. That means that what we're going to do is multiply 2 times everything in our empirical formula, which is CCl2. So we double all the atoms. Now, it's not always 2. It could be 3 or 4. I know it's been 2 the last 2 problems, but it could be a different whole number, but it will always be a whole number. So our molecular formula is going to be C2Cl4. And again, I'm kind of low on space for drawing, so I'll draw it sort of up here in the empty space. We'll put 2 C's and then 4 Cl's. All right, so that was problem number 5. This is very similar to the passing type problems you see on the test. Our last problem, number 6, which let's scroll down to number 6, is a little bit more difficult. It's more similar to an exceeds type problem. And the main difference here is when we do our first step, we're going to find out that we don't get a whole number ratio right away. So we have to figure out how to fix that. So first, let's do the problem. A sample of iron oxide has 1.116 grams of iron and 0.480 grams of oxygen. Its molar mass is 5 times as great as that of oxygen gas. We'll get back to that part. And then find the empirical and molecular formulas. So first, as always, we convert our grams to moles. So starting with the iron, we have 1.116 grams of iron. The other day in class, someone wrote I for iron, and I had a heart attack. I is iodine. Remember, iron is one of the weird ones. It's Fe. You're not allowed to make up your own abbreviations. So when we look up iron on the periodic table, we see that its molar mass is 55.85 grams of iron in every 1 mole of iron. And we need to put the grams on the bottom so they'd cancel. And that gets us 0.020 moles of iron. And then we need to do oxygen. So we had 0.480 grams of oxygen. And oxygen, according to the periodic table, is 16 grams for every 1 mole of oxygen, which gives us 0.030 moles of oxygen. And you may be, if you're worried about sig figs, remember sig figs don't really matter on this type of problem. You don't want to round too much, but there's no sig figs in the final answer. So we will divide to find the mole ratio by the smallest number, which in this case is the iron number. So we'll divide by 0.020. And that will get us 1 mole of iron, but we get 1.5 moles of oxygen. Now we can't round that because it's not close to a whole number. You're only allowed to round it when it's close to a whole number. So we need to think about this and think about how can we turn this into a whole number ratio. So if it is a 1 to 1.5 ratio, how do we make that into a whole number? And it's helpful to think of it rather than decimals as fractions. So this is 1 to 1.5. And if I have a half, if I multiply it by 2, then I can get a whole number. So if I multiply both of these by 2, then I can get the whole number ratio of 2 moles of iron to 3 moles of oxygen. So my empirical formula would be Fe2O3. So when you get something that's not a whole number, and the only time you're allowed to round is if it's within 0.1, like if you had something that was 2.04, you could round that down to 2. But if you have something like 2.25, you're not allowed to round that. And so you need to think about it in terms of fractions so that you can think about what is the lowest whole number ratio. So that is my empirical formula. And now let's go back and think about what it said in the problem where it was talking about the 5 times as great as oxygen gas thing. That was something we threw in there, a little tricksy, because we wanted you to remember that oxygen gas is diatomic. The oxygen we're breathing right now is O2. So to find that, you would say 5 times oxygen gas, which is O2. And we already looked up oxygen earlier. It's 16 grams per mole. So it's going to be 16 times 2 for the oxygen gas. That's for the O2. And when you do that math, you get that it's 160 grams per mole. So that's the molar mass of the whole thing, of the molecule. And now we need to figure out the molar mass of our empirical formula so we can compare them. And remember that is Fe2O3. So we take 2 times the molar mass of iron, which is 55.85. And we add 3 times the molar mass of oxygen, 3 times 16. And when we do that, we get 159.7. Now, 160 and 159.7 are not exactly the same, but they sure are close. So we're going to call that about the same. So we take the 160 and divide it by 159.7. That's about 1, which means that the molecular formula is the same as the empirical formula. It is Fe2O3 as well. So remember, the molecular formula, although it can be different than the empirical formula, it doesn't have to be. Oops. On this very last problem, this is just so you can remember what the two words mean. It says, what are the empirical and molecular formulas of this drawing? Now remember, this drawing, this is the molecule. This is the molecule. So because of that, whatever's there, that is the molecular formula. So if I count it up, I've got 2 H's, H2, and 1, 2, 3, 4, 5, 6 O's, H2O6. So that is the molecular formula. Then the empirical formula is the simplest ratio. Well, both of those can be divided by 2, so the simplest ratio is HO3. So that would be our empirical formula. So molecular formula, actual molecule, empirical formula, simplest ratio. Hope this walkthrough was helpful. I will see you later.